In this unit we begin our look at waves, specifically mechanical waves. Now it doesn't matter if it's a mechanical wave or an electromagnetic wave, waves do the same thing. Waves transport energy from one place to another. It's a disturbance that transfers energy. So an energy input causes a vibration, that vibration moves through something, goes to another location, and then that energy is transmitted. There's two major groups of waves, mechanical waves and electromagnetic waves. We have actually talked about electromagnetic waves before. When we talked about the three methods of heat conduction, we talked about conduction, where particles touch, convection, where particles move, and then radiation, which is heat transferred by an electromagnetic wave. And so radiation is a form of electromagnetic waves. It's heat moving through, well, it can move through air, but it can also move through a vacuum. So electromagnetic waves, light waves, radio waves, infrared radiation, X-rays, gamma rays, those are all electromagnetic waves, and they have the unique ability to move through space. They can move through an empty space. They can move through a vacuum. Mechanical waves, on the other hand, can't do that. Mechanical waves must move through matter. There has to be matter there in order for them to transport energy. And that matter is going to vibrate. That's what we say when we say a disturbance. Okay, so the matter through which the wave travels is called the medium, and the medium is going to vibrate. However, the medium is not going to shift out of position. So the medium vibrates about a fixed point, but the wave does not carry it from one place to another. The energy moves, the wave or the medium does not. Okay? So you guys took a look at these two different waves in lab. You made a transverse wave by taking a slinky and shaking it end to end, so you had these waves moving through. And let's just take a look at an animation of a transverse wave so we get an idea of what's going on. So if you follow just a wave crest, which is the top of one of these bumps, all the way from one end to the other, you'll see that the wave moves this way. So the wave motion is from one end to the other. However, if you follow a particle, you'll see that the particles just vibrate up and down. So the particle vibration, or the vibration of the medium, is orthogonal, or at a right angle to that. So the particles are vibrating up and down, the wave is moving left to right, and we call this transverse because the vibration is across the wave motion. And so in a transverse wave, the particles vibrate perpendicular to the motion of the wave. Longitudinal waves, they don't do that. You guys also made a longitudinal wave when you had your slinky and you pushed it this way and pulled it back, and you had these areas of higher compression. That's what that is, moving through. Oh, it's moving this way. And then you have these compressions and these what are called rarefactions. And so you can see this wave front is actually moving to the right. We have a wave moving this way, a wave moving this way, a wave moving this way. But if you follow just one of these particles, this particle is here, coming this way, coming this way, coming this way. It never shifts out of position. So the wave motion is still end to end. The wave motion here is still this way. But the vibration of the medium is no longer transverse to that, it's parallel to that. The vibration is end to end. And I have another animation here. Let's go ahead and take a look at that one. It's just got the labels put right in it. So we have our wave, this arrow down here is moving to the right, and there's several different particles that are picked out, and you can see if you follow any one of those particles, they just move back and forth, back and forth, back and forth. This compression and rarefaction are also labeled. The compression is where they're all squished together, compressed. Rarefaction is where they're spread out or they have been made rare. And we'll take a look at that in the next slide. But in a longitudinal wave, the particles vibrate parallel to the motion of the wave. Now, here's the parts of the waves all laid out for us so we can see. Remember, this is a longitudinal wave up here. The wave is moving this direction, or this direction, depending on how you look at it. So, like I said, the area where there's not a lot of matter, it's been made rare, that's called a rarefaction. You might also hear it called an expansion. Okay. Where it's all been squished together, that's a compression. And this picture doesn't show it, but if you look at the distance from a compression to a compression, that is called a wavelength. Okay. This is a transverse wave. So again, we have wave motion this direction, left to right, and particle motion up and down. So there's this dashed line here, and we're going to continue it through. That's where the medium will return once this wave goes through. So if the wave passes and there's no more disturbance, it will return to this spot. Now, the maximum height above that spot is called the crest. The distance from the equilibrium to this spot is called amplitude. That's what that shows. From crest to crest is called wavelength, and then the low point of your wave is a trough. Wavelength actually doesn't have to be crest to crest. It can be trough to trough. It is from one identical point to the next identical point. So those are the parts of your wave: transverse, longitudinal, mechanical waves.